Yeah, Assalamualaikum everyone. So today I will do the introduction from my group. So we will do falling film absorber experiment. Okay. So before we show you how we conduct this experiment, I would like to show you some the important part of this system. Okay, this absorber system. So we start with nitrogen tank. Okay. So this nitrogen tank is our nitrogen source. Okay, so the nitrogen will be supplied to this deoxygenator from the bottom. Okay, because we want to deoxygenate the water using nitrogen. Okay, so the nitrogen we will supply from the bottom, and then we have water supply from the top. Okay, so the water will come down and the nitrogen will go up. Okay, so this is where the oxygenation happen. Okay, so this is the two part, and then we have the circulation pump. Okay, we have pump 1 and pump 2. So we have valve. So pump and valve are used to control the water flow rate, and also we use maintain water level in this deoxygenator. Okay, so next we have this one. You have DO analyzer. Okay, so DO analyzer are used to read the data of the experiment. Okay, which is where we get all the results from this experiment. Okay. So and then we move on to absorption column. Okay, so the water that has been deoxygenated will come from the top. Okay, and then we have oxygen. Okay, coming from the bottom. Okay, because actually we have air compressor, portable air compressor outside of the lab, so we cannot show you. So we get the air supply from that compressor, and then we supply it to this absorption column, okay, from the bottom. Okay, so this is actually where the absorption of the oxygen happen lah. Okay, so then we will collect the sample, the product. Fortunately, this DO analyzer broken, so we cannot use it. Okay, so we have portable DO meter. Okay, so to calculate, to obtain the result, we have to do manually. Okay, so we collect the product, okay, the sample, and then we will read the result using DO meter, portable DO meter. Okay, so how to use it, we will show you in this experiment. So before that, okay, I forgot to tell you the objective of this experiment. So we have two. First is we want to study the liquid film absorption of oxygen, okay, in the form of air into deoxygenated water. Okay, number two, we have to calculate the power law relationship. Okay, and then compare with the existing relationship, okay, based on this experimental data. Okay, so I think that's all from me for the introduction. So how we use it, how we conduct this experiment, we will show you after this. Okay, we will conduct by HAFIZ and Azeem. Thank you. We move on to the working theory and equations. Before that, I will explain Reynolds number. Reynolds number is used to determine whether the flow of water inside the system is laminar or turbulent. And then I will talk about Sheward number. In the range of large porosity, the Sheward number, which represent the mass transfer coefficient for transit from a flowing fluid to a swarm of spherical particles, is determined. Okay, but in this experiment, Sheward number is a representation of the ratio of mass transfer by diffusion to mass transfer by convection. So there are the formula used. We have molar flux of oxygen equal to Kw, and then times C2 minus C1, and then times by MWA. Okay, so these are the list of the equation we use in this experiment.
In this step, we are opening our valve V1 and set the air flow rate to our desired flow rate. We also need to monitor our water level in the deoxygenation column by adjusting our V3 valve. The water level in the deoxygenation column will always fluctuate. Hence, we need to monitor both valves simultaneously. For data collection, we open valve 6 located at the top of the absorption column to collect water sample that has not undergone adsorption. Since we are collecting our water sample before undergoing the absorption process, we are expecting our water sample content is low with oxygen concentration. Now we are using our portable DO meter to analyze our sample dissolved oxygen content. Now we are repeating the same step for our next sample. However, for this time, we are opening our valve 7, which is located at the bottom of the absorption column, in order to collect our water sample. This time, we are expecting our sample concentration of oxygen to be much higher, since the water has already undergone absorption process. Again, we are using the portable DO meter to determine the dissolved oxygen level in our water sample.
Now, we are going to discuss about the result and discussion. This is table 1, which contains the raw data from the experiment and molar flux of oxygen. The raw data from the experiment include DO sensor 1 and DO sensor 2, while the molar flux of oxygen can be calculated using this formula. Next, this is table 2, which contains the raw data from the experiment and average concentration difference. The raw data from the experiment is the same as the table before, and the average concentration difference can be calculated using this formula right here. Moving on to the table 3. Table 2 contains molar flux of oxygen and average concentration difference that we have calculated using the formula before. This is liquid mass transfer coefficient that we can calculate using this formula. Now, this is table 4. This table 4 contains the Reynolds number and Sherwood number, which we can calculate using this formula. This is figure 1, which shows the graph for Sherwood number versus Reynolds number. Moving on to the discussion, first, setting up the experiment. Few parameters were kept constant to get the desired result. The parameters that were kept constant include the volume of oxygen entering the absorption column and the flow of nitrogen. Flow rate of water into the absorption column through SB2 was set as the manipulated variable. The flow rate of water was set to 1,800, 600, and 400 ml per minute. The water level inside the deoxygenated column was adjusted and observed at all times to get the consistent water level throughout the experiment to get consistent results. Now, we will discuss about how to obtain the result. Samples collected from the assigned valve were tested using dissolved oxygen, OD meter. The OD readings for C1, which is the inlet, and C2, which is the outlet, were tabulated, and these values were used to calculate the molar flux of oxygen into the water film and liquid mass transfer coefficient using the appropriate formulas as I have shown before. Next, result discussion. The result shows that as the water flow rate decreases, the dissolved oxygen content also decreases. This is because the diffusion of oxygen decreases when less volume of water is flowing inside the absorption column. This is justified from the result, which indicates a decreasing trend as the flow rate decreases. This is also justified by Kokzaru and Ingilizakis 2015, who state that liquid mass transfer coefficient is a flow-dependent parameter. So, as the flow rate decreases, the mass transfer coefficient of oxygen into the water will also decrease. The Reynolds number is used to determine whether the flow of water inside the system is laminar or turbulent. Meanwhile, the Sherwood number is the representation of the ratio of mass transfer by diffusion to mass transfer by convection. The direct proportional relationship between water flow rate, Reynolds number, and Sherwood number was concluded to be as the amount of water flowing into the absorption column decreases, Reynolds number and Sherwood number will also decrease. Figure 1 shows the linear relationship between the log of Reynolds number and Sherwood number, and the gradient and intercept value were calculated as 1.2 and 0.67 respectively. This value are similar to literature value. Thank you.
So now let's look at the conclusion and recommendation for our experiment. So the falling film experiment investigated at how rapidly air oxygen may enter the oxygenated water. As water flow increased, the molar flux decreased until negative values were obtained. And where the flow rate was larger, the values of the Reynolds and Sherwood numbers were increased. The power law relationship plot, which was graphed at the end, showed a positive association between log Reynolds numbers and log Sherwood numbers. The constant of the power law applied in the experiment to correlate the mass transfer coefficient to fluid parameters were found to be at A 0.67 and our M is 1.2, which is similar to the value found in a literature review. Next, for recommendation, in order to obtain more accurate data, the results for future performances, it is recommended to increase the number of experiments with greater flow rates in order to eliminate this error. This will give power law relationship analyzes more precise assumptions. Another method is to design an experiment from earlier research so that the results may be compared under identical conditions, and we can get a better understanding of how well the falling film unit absorption works by measuring the error value. And lastly, to get much more accurate data, we can the equipment we can use to measure the oxygen level can be replaced with a new one, the DO meter. So that's all for the presentation of our group. Thank you very much.